Okay. Can you see my presentation?
Yes, we can see it. Yeah.
Okay, so thank you once again for having me. It's really a pleasure for me, as I was telling you shortly before. So my talk of today is titled Leveraging Mixed Experts for Improved Speech Detection, which is also the title of one of the two papers that I'm presenting you today. Both are about, as you can imagine by now, mixture of experts, which are a particular framework that you can employ in several fields, including the speech defect detection one, which is the one where I work mostly. So before starting, I would like to introduce you guys to our laboratory a little bit, because I bet that nobody of you almost knows us. So it's good to introduce ourselves before starting. So as Brie was saying, ESPL stands for Image and Sound Processing Lab. We have a lot of people working in this lab, but I work especially with these folks here. We are the forensics division. Professor Stefano Tubaro is the leader of our group, and his right arm is Professor Paolo Bestagini, which is also my supervisor. Then, as you can see, there are several researchers. There is Sara, that she's the senior of the group. She deals with the image and video forensics, along with Giovanni, which is a PhD student like me. Then you can see that there are also some people that deal with a slightly different research topic, which is geophysics. But I'd say that after all, the very thing joining us all is signal processing. So this is why we're all together in the same division, because we all are signal processing rooted. So we took different paths, but we share the same basis. And then there is me, of course. And I deal mostly with audio forensics. So this is, this was the audio team up to some months ago. On most of my papers, you will see also Davide's name, Davide Salvi. He used to be my senior colleague in the audio team. It was just us, so I think it was a good choice also to introduce him to you guys. No, he recently transitioned, but on most of my work, so you will see his name. So, but anyways, now it's just me in the audio team. So it's needless to say that I feel quite alone. So of course, I'm very much open to connect with you guys, share ideas, collaborate on works, not only of mixture of experts, of course. So feel free after the talk or whenever you feel ready to drop me an email or write me on LinkedIn or whatever. About me, there is not much to say. So as already has been mentioned, that I'm a PhD student. I'm completing my second year. I'm specialized in audio forensics, but I deal mostly with speech defect detection. So far, I published 10 papers. I got 3 more under review right now, so fingers crossed. And here I just reported a couple of works that I did that I'm particularly proud of. If you're curious, you can check them out, or you cannot, as you prefer. The first one is actually my first published paper, while the second one is a more recent one. It's about source tracing, and it was published in interspeech proceedings of this year. So. But anyway, let's finally delve deeper into today's talk. So this is the outline that I'd like to propose to you. We will start, of course, with the motivations behind these two papers that I'm presenting and the use of mixture of experts in our field. Then I will touch a little bit some background about MoEs, so mixture of experts, just to get you guys an idea of how these frameworks are structured. And then we will finally go through the papers. So the first one was published in the ICASP proceedings of 2025, so this year. And we will briefly touch the rationale, the proposed systems, of course, the evaluation setup that I used, and the experimental results that we've got. Then we will pass to the second and last paper, which is titled Attention-Based Mixture Experts for Robust Speech Defect Detection. And that is a paper that's about a system that we used during the spring to win a challenge that I will briefly talk about. And we will again talk about the system, the evaluation setup and the results, and then we will finally be able to draw some conclusions and also some limitations of this work. And then as a conclusive remark, I will leave you with some ideas that I have about MoEs, some future directions that we might take as a community. So this will conclude my talk eventually. Okay, so motivations behind the use of MoEs in speech defect detection, but in general of the need to work in this field. So I think that everybody here knows that text-to-speech and voice conversion tools are getting better and better and easier to use also by people who has basically no experience at all in signal processing, AI or deep learning. And for these reasons, frauds, scams, and other crimes, all relying on generated audio, so synthetic audio, are skyrocketing, and that is unfortunately a fact. My personal opinion here is also that audio in comparison with image and videos, but again, this is my personal opinion, is that audio is actually might be twice as stealthy as for other media, because audio, if you think about it, often carries some kind of an implicit sense of authenticity and intimacy, and it comes natural to us to instinctively trust a familiar voice, whatever. So this might be related to the fact that we hear long before we see when we are born, but again, this is my opinion. You can agree with me or disagree on this, but it would be nice to have a chat on that. So anyway, this is the situation. It's bad, and it's even worse if we think that most of the speech defect detectors that we use now in the academic landscapes, if taken and tested as they are in real-world conditions, so in the wild, they systematically underperform. Why do they underperform? Well, I bet that you know which are the most common reasons behind it, and they are basically two. The issue of generalization and the issue of robustness. So starting from the generalization problem, which is the most, I think, important one. What does it mean when a detector cannot generalize? It means that you got your detector, you train it on your training data, the ones that you manage to collect. But then when you test this detector on data that you don't know, that it has never seen, so that are quite different from the one that it has seen during training, well, it will give you the results that are worse than the ones you got in domain, that is a technical term, and possibly also bad in absolute terms. What do I mean by unknown data? Most of the times we refer to unseen synthetic speech. So synthetic speech, deepfake, that comes from generators that are very much new and that you couldn't include in your training set. But also new data can refer to genuine data that it's very much different from the one that you see during training. So maybe genuine data, real data from different languages with a very different accent from the one you saw, and so on and so forth. Another very important thing we should not forget when we talk about generalization is the shortcut artifacts problem. What is that? Most of the times the problem is related to unseen data, but sometimes, and this is something that I think it's quite underestimated nowadays, the detector may not be able to generalize very well because during training it has learned shortcuts. So it didn't, in our case, learned to recognize artifacts that are typical of the problem of speech defect detection, but rather it's grasped some kind of elements and patterns that are collateral, that has nothing to do with the problem at hand, and that it is probably not present in the test data that are different from the training ones. I refer to the problem of the duration of silences, of the peak amplitude of the signals, and there are many others. So a quick suggestion that I would like to leave here for you guys and also for me is to always double check our training data, to check the literature about shortcut biases and so on and so forth. As regards the robustness problem, this is quite different, but similar to the generalization problem. I will be much shorter here. A detector that does not generalize is a detector that, again, performs very well on the data that it has seen. But when you do some tricks on this data, which can be post-processing with codecs, adding noise, or even try to test some data that is similar, but that has undergone some kind of degradation, maybe when sharing on social media, well, this detector at this point underperforms. So it's quite similar to the generalization problem, and it's a very different thing. Robustness has to do with data that are potentially in domain, but that slightly shifted from your domain because of these processed operations. Generalization, these are just going where they want, but generalization, as I was saying, is about new data. So data that you didn't see, the data that are out of distributions. So which are some common solutions we can adopt to solve this problem? Well, the most straightforward ones are, of course, fine-tuning and joint training or retraining of a single detector. Fine-tuning, we all know, has a very huge problem, which is catastrophic forgetting, while retraining a single detector on new data as it comes, of course, is a solution that, if you think long-term, is not scalable. So a very suitable solution to these problems, which does not include the straightforward ones, is the use of mixture of experts framework. So let's go through very quickly some background about MoEs. So here in this slide, I reported some relevant literature that you might be interested in when it comes to mixture of experts. The first is the first paper that introduced this kind of frameworks. And it's interesting to see that it dates back to 1991. So it's a quite old paper. And this means that MoEs actually have been around for quite some times. And in fact, indeed, they are well-established frameworks in our deep learning and AI field. You can think of natural language processing. Deepfake is a mixture of experts, as you probably know. But in our field, they haven't been in our field, I mean, my field, speech defect detection, they haven't been explored much. So this is why I'm here today in 2025, almost 2026, talking to you about mixture of experts. Then the second paper that I reported here is just a literature survey, which is the one that I used to get some knowledge about MoEs in the first place. It's very well written, clear. I strongly suggest you to engage with that as a first reading on MoEs if you're very interested in these frameworks. Well, the third one is a much newer paper. It dates back to 2017, and it's actually about mixture of experts layers. So it's not about the very specific framework that I will discuss shortly. It's a different kind of MoE, but I think it might be very interesting for our community to know and to use, especially because we are about to introduce as a state-of-the-art very huge models. But we will talk about this at the very end of the talk. So now let's get deeper into the topic finally. So what are the core elements that distinguish a MoE framework from every kind of other framework so you can encounter in the landscape? Basically, there are just two elements. One are the experts, and the second one is the gating network, also known as gating function or gate. You can call it whatever. So it's quite few pieces. It's not very difficult to recognize a MoE. So what is an expert? An expert is a model that is specialized in a specific domain of the data or representation of the data it is trained on. while the gating network is a controller model. So another model whose purpose goal is to analyze the input again, and by looking at the input, dynamically determining the contribution of each expert in the framework to the final output, to the final decision. So in a MoE, there is one single decision, and it's put together by the gating network by looking at the input and the experts. Besides that, we might say, I think we can say that there is not much more we can say to narrow down a MoE profile. Why? Because flexibility is actually the key characteristics of these frameworks. So you have experts, you have a gating network, but the way you put them together and how you put them together, it's basically up to you. There are multiple, almost endless configurations. And here in this slide, on the right, I reported to you a very simple MoE prototype. This is a structure which is basically the standard one, and I took this image from the survey that I was telling you about shortly before. And you can basically see that here we have experts that are MLPs in this case, so one of the most easier choice you can make. They both look at the same input, which is X, and they produce output, which are probably logits O1 to ON. Then you got the gating network that looks at the very same input and produces G1 to GN weights that are used to put together the decisions of the single experts to the final one through a softmax and a summation. So once you choose the framework, as I was saying, there are multiple choices at this point that you can make that you may prefer or not, and depend entirely on you. So first of all, you can choose how to partition your training data among the experts, meaning that you can do it in a deterministic way or in a stochastic way. You can decide whether to train the expert pre-training them before training them again with the gating network, or you can pre-train them and never train them again with the gating network, so use them frozen. Or again, you can choose to train them from scratch together with the gating network. Then another thing you can choose, and it's up to you, is how to put together the logics of the single experts, of course. So the standard choice is using a soft gating, so taking into account every expert's always on every decision, but you can also opt for a top K approach, for example. But nevertheless, what I'd say is that this is just a prototype of MoEs, and then you can pretty much play with them. And this is why I personally like these frameworks a lot. So when it comes to MoEs in the speech deepfake detection domain, there are some choices that are easier than others. For example, as experts, the standard choice and the easier one you can make is choose as expert a synthetic speech detector, of course. So you can choose a traditional one, so ResNets or LCNNs that are still very much used in our field, even though derived from the image domain. You can choose the SyncNet-based networks, which are basically RONet and ASIS. There is also ROGAT, but it's not as much as used as these ones. Or since we are in 2025, you can use self-supervised learning backends, namely Wave2Back, XLSR, but also Ubert, Beats, whatever you like. You can use them alone. You can use them, as you know, with a detection backbone like ASIST. It's up to you. When it comes to the gating network, on the other hand, here the choice is very wide, meaning that there are no rules. You can choose a proper model, like a neural network. I used the neural networks, a very simple one in one case, and the transformer based in the second paper, but it's not necessary. You can also use a bunch of functions and do not take into account, neural networks at all. So finally, let's start talking about the papers that I'd like to introduce you to today. So this is my first, our first paper on mixture of experts. As I was mentioning, it was published in the ICAS proceedings of 2025. The title is the same as this talk, and this was the first paper, again, to the best of our knowledge, that introduced a mixture of experts in our specific domain, so the speech defect detection domain. Some examples already existed in the image forensics and video domain. I encourage you to look them up if you're interested. There is much more literature in those fields, as it happens often when you deal with forensics. They're much more ahead of us, so we're trying to keep up. But anyway, let's discuss a bit the choices behind the systems that I'm about to present to you. So as I was mentioning, MoEs are very flexible. So in the first place, what we have to do is to narrow down the choices and chooser fighters, as we say. So first, the partitioning of the training domains. How did we do? We decided to partition the domain deterministically. What does it mean? That we split the training domain before training and assigned every partition, every split to the expert in a predetermined way. So each expert in the configurations that we will see was assigned a domain before training and was pre-trained on this domain before being again trained jointly with the gating network. So we let them update, but we pre-trained them on a domain. What is a domain? In this case, it's simply a synthetic speech dataset. So we used, in this case, I guess, 4 different speech defect datasets during training, and we will see them shortly. Then other choices, the important choices that we made, well, it's basically one, we chose to maintain soft expert selection. So there is no hard gating here. Every expert contributes always for every input speech to the final decision. And so basically we apply the softmax and averaging as the literature suggests. So these are the systems that we propose in this paper, the standard MoE and the enhanced MoE. Well, the standard MoE, if you look at the design, is pretty much the very same network that I reported in the prototype a few slides ago. So there is nothing different here. There is a gating network and there are 4 experts. And each of these elements take as input the input speech sample. Also the gating network. The gating network produces the weights, so alpha, that are multiplied with the logits produced by each expert. So they're put together and you got your final output. So 0 in our case is for real and 1 is for fake. On the other side of the slide on the right, you see instead an enhanced MoE. I mean, we call it this way, but it's just a different kind of MoE. It's enhanced because it was a name we gave to it a posteriori because it performed better than the standard one. So the main difference here, as you can see, is that the gating network here does not directly look at the input anymore, but rather it takes as input the embeddings coming from each expert. So the expert, we extract from each model the hidden representation, well, it's actually the embedding from the last fully connected layer. And the gating network makes a decision based on these internal representations. And then the second part is exactly the same because it still produces weights that are combined with the logits and so on and so forth. So this is the evaluation setup that we used. As I mentioned, we used 4 experts, so 4 different training dataset, namely ASB Spoof in 2019, Fake or Real, In the Wild, and ADD 2022, because we wanted to try to include at least one different language in the framework and see how they would behave in this case. Then we tested, of course, in domain on the evaluation partitions of these known domains, and out of domain on the Purdue dataset and the timid TTS dataset. I don't know if you know this dataset. The Purdue one was a very recent data set at the time, so last year. It basically only comprises synthetic speech that comes from voice conversion tools that are diffusion based, while the TTS, as the name says, only comprises TTS speech plus genuine one, of course. So we got to quite two different unknown testing domains. As for the architectures that we used for our frameworks, both the standard and the enhanced MoE used as experts one single kind of speech defect detector, which is the LCNN. Why the LCNN? Because it still works very good as a synthetic speech detector, and it's most importantly very lightweight and train fast. We needed something that trained very fast. As for the gating network, the design was kept super simple. So it basically comprised, in both cases, just a single or a couple, I don't remember correctly. I think a couple of dense layers, dropout, batch normalization, of course, and slight nonlinearity represented by the leaky ReLU. We compared, of course, these frameworks with the performance of the individual experts first, but also with some baselines, and the most, easy choice in this case were the averaging ensemble, of course. So something like a MoE, but that does not dynamically put together the outputs of the experts, but rather uses a fixed strategy. So in this case, the average. And an LCNN, second baseline, that was jointly trained on all the known domains. So a single model here. Let's finally get to some results. This is a very huge table of results, but it's actually very easy to go through. So the first 4 rows are the performance of the individual experts on first the 4 known domains, their evaluation partitions, of course, and then the 2 unknown domains. Then you have the performance put together on known and known plus unknown domains. Then you got the ensemble, the joint training, and the proposed MoE, which refers in this case only to the enhanced MoE framework. I removed the standard one to make the table a little bit lighter. But if you're interested in to seeing the performances of the standard one, you can look at them in the paper. So what we can say about the results regarding the individual experts, they, if you look closely at the results at the table, perform very well, of course, on their known domain. But when it comes to infer, so whether an input sample is real or fake on different domains, you can see that the performance is like hugely drop. The ensemble and the joint training, of course, are a bit more robust, I'd say, generalizable, better to say, in these cases, because they still leverage or multiple experts or an individual model that knows a bit about every kind of data. But eventually it is the MoE framework, and I just suggest you to look at the last results, the averaged ones, that performs much better than all the systems in this table. And this was a very surprising results, I'd say, particularly in comparison with the joint training, because this confirms a suspect that we had that was, okay, joint training is an easy choice you can make, but the suspect is that when you train a single model on a lot of different data, scalability may start dropping off at some point. This is probably exactly what happened. The capacity of a single model stretches at some point, while a MoE can accommodate for a much wider representation of much more data. If you were I mean, if you noticed in this slide here, just look at the results about the MoEs. The performance on known domain is actually strangely lower than the ones on overall domains. Why? You see there is a 92.87% AUC versus a 93.95. And this is quite strange because you would expect that including unknown domains would drop your performances. Why did this happen? Because there was I mean, by chance, we included in the training domains, among the training domains, dataset that happened to be particularly challenging for our framework, which is the ADD. So the ADD 2022 dataset. And this is evident also, sorry for switching back and forth. If you look at the performances of the expert trained on that domain, you can see that him itself could not perform very well, and it just hit a limit at more or less 70% of Chi, which is pretty strange for an in-domain results. And a very, very interesting thing about MoEs that can help us, draw more conclusion about this kind of dynamics is that you can leverage some kind of interpretability. In what sense? In the sense that you can analyze the weights of the MoE, of both the MoEs, of every kind of MoEs, and by, in this case, taking the average of the weights on every single domain, you can see which expert contributed more in that precise domain. So you can see that in these plots, for example, for the ESV Spoof 2019, Fake or Real, and in the wild, within the enhanced MoE, the experts that were queried the most were actually the ones that were trained on those domains, so ASV, for and in the wild. But if you look at the average gating weights on the ADD dataset, you see that the ADD expert was not the most queried one, but it basically on par with the in the wild expert. This is a very intriguing and useful property of MoEs, meaning that if you have an expert that from some several reasons is underperforming in its domain or it's underperforming in general, MoEs have the ability and the strength of compensating with other experts. So in this case, the MoE, the framework found out that the most suitable expert to substitute the ADD1 was in the wild. So it queried that, it gave progressively more weight in the decisions about the dataset to the in the wild expert. And it's of course, it's also interesting to see on unknown dataset, which are the most interested and involved experts. So in the case of the Purdue dataset, this is a even more strange thing. The most queried expert was the ADD1, so the one that underperformed on its training domain, while on the TMTTS, there is basically an even contribution of all the experts. So contributions so far, we showed that MoE can be employed successfully also in the speech defect detection domain, and that they can actually improve by far the performances holding to a wider generalization than traditional solutions. And also, as we saw shortly before, we can draw some conclusions in terms of interpretability thanks to these frameworks. So they are also very valuable for explainability and again interpretability, which is a very much desirable properties nowadays. Okay, so we finally reached the second and last paper that I'm about to introduce you to today. This paper here was accepted very recently, last month, at this conference that is called, it's an IEEE conference, and it's called the International Workshop on Information Forensics and Security. I don't know if some of you know it, probably not. So I just would like to encourage you perhaps to look it up, because it's a very small conference. Again, it's a single track conference, but you can find actually very interesting works besides this one, of course, but I really suggest you to check it. If you are coming, which because this year's edition is gonna be in December in Australia, if you're coming, maybe drop me an email. We may chat a little bit while there. I'll be probably alone, and also come to the tutorials on Monday because I will host one probably. So anyway, back on track. So as I mentioned at the beginning, in this paper, we presented a system that we used to win a challenge. The challenge is this challenge here, the SAFE challenge, that stands for, it was the first edition of this challenge, so you probably do not know it. SAFE stands for Synthetic Audio Forensics Evaluation Challenge. It was held in the context of information hiding conference, and it comprised 3 different tasks. All the tasks had as main goal synthetic speech detection, so speech defect detection. It was interesting because it had a completely blind evaluation protocol, meaning that no training data nor test data were released. So you had nothing to train and to test your detector. You only could submit your scores. I mean, your model on a give face. And then the teams, participating teams, were ranked based on the balanced accuracy metric. It's another interesting thing, so a threshold metric. And here I'd like just to drop a note, because as you can see, there were just 10 teams participating and engaging into the conference this time, and also the video challenge that the same organizer organized didn't see much participants. So I just say, guys, and try and engaging in challenges. I'm a shy person, so I was basically forced to to participate to this challenge. But it is true that they are very useful, both because they allow you to test your frameworks on real world scenarios, so you can get to see if they really work or not, but also because they gain you visibility, of course, and they allow you also to network with people that deal with the same things that we do. So let's try to participate in challenges. So these were the tasks of the SAFE challenge here. As I was telling you, they're all about deepfake detection. The first one comprised clean audio, so it was pure detection on clean data. Genuine data was from 21 different real sources, so you got to have a detector that was very well at generalizing, and 13 different TTS model, new generation 1. Then task 2 was always binary detection, but fake data in this case were post-processed, so basically through codecs. And the third one was similar to the task 2, but this time data were laundered, basically. What we did very bluntly was focusing on task 1. So we tried to win task 1, and then we basically just submitted that very same system to task 2 and task 3. This is why you will see very good results on task 1 and not so very good results on task 2 and 3. So about the system that we proposed. This here in the slide is the enhanced MoE from the previous paper. So again, we got in this case an a priori partitioning of the training domain. So we got identical experts with different training dataset, and we showed that this system can lead to a strong generalization and interpretable also some kind outcomes. Research question here was, okay, can we use this model for the challenge? Can we boost its performance even more? The answer is, of course, yes. And what we did after seeing that the very first configuration, so this one was not winning, we introduced 2 key changes in this framework. So the first one is the easiest to understand, and it's simply a different design for the getting network. So we had, as I told you, a getting network that comprised simply a couple of dense layers. In this case, we decided to get transformers into the equation. So we employed an attention-based getting network with a couple of transformer layers. So nothing heavy, nothing huge, just an incorporated attention-based mechanism. But the second change that we introduced is the most important one, and is a paradigm shift from a so-called Mealy framework to a so-called Miley framework. Basically, what does it mean? It means that we passed from a situation where we had identical experts, so 4 LCNNs trained on different datasets, from a situation, a framework, where we have different experts, but trained on the same pooled training domain. Okay, so here you can see what these names stand for. Mealy, which refers to the ICASP framework, stands for mixture of explicitly localized experts. So what I was just saying, different domains, the same experts, while Miley stands for mixture of implicitly localized experts, different architectures trained on the same data. In this case, it's important to underline that we had 3 experts and not 4. Why 3? Because we experimented with a bunch of different configurations, and this one here that I'm about to present, it was the best one. So, and this one comprised only 3 experts. An important side note, I said expert architectures, but by architectures in this precise case of this paper, I mean feature plus model combination, meaning, we will see shortly what I mean. So here there is just a visual recap of the distinction between these 2 frameworks. Note that the Miley here reports 4 different experts, but as I was telling you, we use only 3. This was just for symmetry. So again, Mealy, same experts, different training sets. Miley, different experts architecture, again, and same training sets. Okay, so this is a little bit more in detail, the system that we presented in this paper and the system that won the challenge. Again, we got this implicit expert localization that we can define in a more formal way now. What does it mean, implicit localization? It means that system stochastically partitions the data domain by leveraging the architectural biases of all its distinct deepfake detectors. So you train all your models. What does it mean? You train all your models on the same data. The models are different. So what happens here is that in theory, the pooled training domain is split among the experts based on their architecture, meaning they will be more or less inclined to look at some parts of the input data. So this is how the split is implicitly performed. You let the network learn this. As you can see in this design, you can also see explicitly how the getting network was designed. So there is basically here the scheme of a standard transformer architecture. So a layer norm, a multi-head self-attention block, a skip connection, followed by another layer norm and a multi-layer perceptor. This is a standard transformer layer. And in this case, in this system, we employed 2 sequential transformer layers. And this was, again, a choice that was taken empirically. Okay, so coming to the setup that we employed slightly, of course, different setups for the challenge and for the experiments of the paper. So the main differences here are, of course, in the training data sets, meaning that you can see on the left that for the challenge, we included a lot of different kind of data, especially real ones. So in addition to the first 4 data sets that are shared with the paper setup, we also included Libre Speech, LJ Speech, VCTK, a common voice for real speech, and DFSSD for to include some new generation TTS, I guess. TTS or also voice conversion tools. I don't remember exactly, but it's a much recent data set. Then another difference between the setups is that we, of course, had to use the data augmentation for the challenge. So in this case in particularly, we used the spec augment and some noise injection using robust that you probably know. But we decided to discard this data augmentation for the paper setup because this allowed us to make a more clear evaluation and benchmarking of the system with the previous one that he proposed. As for the expert architectures, I already talked about the Getting Network. Let's now put on the table the experts. As I was saying, here with architecture, I refer to a particular combination of model and feature set. Indeed, you can see that we used as 3 experts an LCNN fed with MEL spectrograms, a ResNet fed to MEL spectrograms. So here we have 2 different models, but same feature set. And then again a ResNet, but fed this time with a log spectrogram, log amplitude spectrogram. So the hope here was that 2 ResNets given that they were fed with different feature sets, would focus on different parts of the input. And this is pretty much what happened if you look at these results. These results are the outcomes of the proposed system on the public evaluation set of task 1 of the challenge. And it's the only task of the challenge and split, so public 1, on which I have the results also for the single expert. And in particular, as I was saying before, you can see that the ResNet MEL spec and the ResNet log spec behave similarly, but not quite in the same way. For example, you can see that on pristine data, you got a detection rate that is much higher for the ResNet fed with a linear axis on the frequency 1. And overall, again, as we observed in the first work, you can see that the MoE eventually gains the higher result in terms of balance accuracy, which was the important metric. So outperforming basically all its single components. In this slide here, I reported the results again on task 1, but of the public and private evaluation set put together, broken down by source, both for real data and for fake data. There are also the results of the other 5, so 6 best performing teams. And it's interesting to see that the MoE that we proposed led to a huge generalization capability, especially, and this was surprising also for us, as regards the real source data. We included a bunch of data sets, that is true, but most of these data sets, beside MLAD, were, for example, English data set. Accents are not very variable, as we know in the English data that we have. And so it was a very nice outcome to see that we hold tight on basically most of the real sources besides the Arabic speech corpus. Why? Because we failed to include Arabic languages in our training set, and probably there was no language similar in terms of semantic structure, syntactics to this one. On the other hand, on fake data, also we can trace strong generalization capability, given that some of these generators were not even present in the ones that we trained on, because we used a lot of different datasets again. But for example, OpenAI and also here speech 11 labs, which we performed very good on, weren't present in our training data. So they were completely unseen and we managed to perform very well. These are the results instead on task 2 and task 3 of the challenge. And while you can see that on task 2, so on the left side of the slide, we managed somehow to hold tight, meaning that we lost only 7 points in terms of balanced accuracy. On the other hand, on task 3, which include the laundered audio, and with laundering, you see now what the organizers meant. So they involved basically the speech tracks with car noise, play reverberation, and so on and so forth. You can see that in this case, our framework, well, there is much room for improvement, I'd say. We still did not fall into a random guess scenario because we managed to keep some discriminative power, but there is much more to do in this direction. Then last results slide, finally. These are results from the paper, because after winning the challenges, the challenge, of course, what we wanted was to give this system a systematic evaluation and frame it within the existing literature. The existing literature was our previous paper. So you can see in this table, especially the first one, a comparison of the proposed model, which is the last one, the one highlighted in yellow, with the system, the enhanced MoE from the previous paper, which is here named as MILI-CAT. So MILI, previous framework, CAT, because just because the gating network was basically concatenation based. And again, you can see also the results for the individual experts of the MILI-CAT, okay? And by looking at the average metrics, it is clear that the system that we've introduced here, improve the performances by far, especially on unknown domains, but also on known domains. The second table instead is further ablation, I'd say, meaning that the first line always corresponds, the highlighted one always corresponds to the proposed framework. The second one refers to a MoE adopting the previous framework, so a MILI paradigm, but equipped with an attention getting network. So basically the enhanced MoE of the ICAS paper with the transformer-based gate, while the third one is the new framework, but equipped with the old getting network. And you can see that again, the proposed systems is the one that performs far better than the other two. So both the changes that we introduced, the paradigm shift and the new getting network contributed actively into reaching the results that we reached, also into winning the challenge. Okay, let's finally draw some outcomes and limitations here. We saw that on the positive side, MoEs hold more capacity and can be significantly more robust than individual detectors. We saw also with this last work that different theoretical frameworks, Mille versus Miley, can offer equal valuable contribution to SDD, so speech defect detection, and that an attention gating mechanism can make a difference. So it's worth designing and think of an interesting design also for the gating network. On the negative side, as you can imagine by now, is that MoEs flexibility makes systematic ablations and studies very difficult. And what we did with this paper is likely exploring less than 1% of what's possible in speech defect detection with MoEs. These works were employed very simple MoE frameworks and were very preliminary works. They were just the basis, I'd say, for the use of MoEs in our field. Also, if you noticed, it seemed like with this last paper, we lost something that we had in the previous one that we cannot afford to lose anymore, which is interpretability. By not assigning different data set to different experts, it is difficult to a posteriori understand on each data set which expert contributed the most. I mean, it's basically impossible. Is interpretability really lost in Miley framework? I'd say no, and we will see now why I think it's not lost at all. So future directions for MoEs. These are just suggestions. I am right now exploring some of these directions. So if you plan to work on MoEs, if you got interested, again, please feel free to contact me because I, of course, am still active on the topic. So the first thing, and some folks already did that, is including SSL models in the receipt. So wave to back XLSR because they are state of the art and it is worthy to say how MoEs behave with this kind of models. Also because MoEs are designed, are very much suitable to work with also big models. Then it would be, of course, necessary at some point to systematically evaluate expert combination and training strategy. And here are some suggestions. So it would be nice to see how the same experts with different feature sets behave, how different experts with the same feature set behave, if pre-training is always necessary, as in our case or not, if maybe a distinct loss functions for the expert and the gating network may be useful. I used just one, but maybe it is worth checking. And again, it is necessary also to investigate the optimal number of experts. So also exploring a sequential addition of experts, monitoring the complexity versus gain in terms of performance would be an interesting research direction. And in this direction, again, I think it will also be quite interesting to see how MoEs could be integrated in a continual learning scenarios. There are already works in the image domain that use the MoEs or frameworks that are similar to MoEs in continual learning scenarios. So bringing them to the speech domain would be interesting. And I'm actually now working on something like that. So in this direction, there is much to explore. Again, it would be worthy to explore and to test a hard gating mechanism, as I used only soft weighting mechanism. So that's another direction again. Then, and here I link again to the literature that I proposed to you at the beginning of this talk. I proposed to you 3 different papers. The third one was about MoE layers, which is a different kind of MoEs. And it would be interesting to explore this kind of MoEs also in a speech defect detection domain because they are designed for large heavy models, and we know that large audio language models are about to take over also the speech defect detection domain. So this is something to look at, of course. And these are some additional directions in this regard. And then, of course, I think the most important thing we should explore is the interpretability of MoEs because they hold much potential in this direction, as we saw. And what I think is also that Miley's, so Miley configuration, like the one in the last paper that I presented, might be actually more suitable than Mealy for interpretability. Why? Because if you actually carefully choose your expert, carefully design them, you can always a posteriori draw some cues on what led to the final prediction based on the characteristics of these experts. An extreme case here would be to design experts with extreme biases. So you deliberately choose experts that are biased in a direction or another, and you see which one is most often taken into account when inferring a decision. This, of course, will impact probably performance, but it would be a huge kick in the interpretability direction. Thank you. We are finally reaching the end of this talk. If you have any questions, I'll be more than happy to answer.